Today we will continue in talking about the flexural analysis of beams. Last time we gave some introduction about the flexural analysis of beams and the fundamentals of concrete, like the modulus of rupture, modulus of elasticity, and we talked about the cracking moment, right, and what does it mean. Today we will cover two things that are essential. Well, one is the next stage from the cracking moment, which is called concrete elastic stress stage, which is the M service. And we will talk about also the transform section method. It's a method to compute the steel stresses and concrete stresses. Right. So, talking about these two, first we have to understand that the graph here that we are talking about is essential to understand, because from the cracking moment, that was the last class. Now we're moving to the M service, right? And M service is the stage where it's between the cracking moment, between the elastic stage, and there are no cracks of concrete till the yielding, where the reinforced bars yields and the concrete is totally crushed in the tension side. We'll come to know about it. So, talking about the M service is normally occurs under service loads. What do we mean by M service? It actually occurs on service loads. So we have a load in the beam here, right? Here is the M crack, and in this stage, M crack is greater than the moment exerted by the service loads. So that was the last lecture that we talked about. And then when the moment exerted by the load exceeds the M crack, then cracks will start to appear. That's what we said in the last class. But actually, this moment that is higher than M crack is the M service that we are going to talk about. Right. Going back here. So when we talk about stress strain diagrams and when we talk about the concrete, we all know that we assume that the bonding between steel and concrete is perfect. That's the assumption, because they both have the same thermal expansion coefficient, right? So when we say stress in concrete equals to, right, it equals to the strain in concrete multiplied by modulus of elasticity of concrete. And we know the modulus of elasticity of concrete from last class, it is equal to, you can calculate it, we're just saying 57,000 radical Fc prime, right? And stress in steel is equals to strain in steel multiplied by the modulus of elasticity of steel, which is fixed. It is 200 gigapascal or 200,000 megapascal. But we have to know something. These two values, because of the perfect bonding, that what we said, are equal, right? So does that mean the stress in steel equals the stress in concrete? No, because the modulus of elasticity varies and they're not the same, right? So that means we have to there is something that we introduce here called modular ratio, which is called modular ratio, which is actually the modulus of elasticity of steel divided by the modulus of elasticity of concrete. What does this mean? What's this term modular ratio means? It means, if let's say if the modular if n was 10, right, this means that the stresses in concrete are the stresses in steel are 10 times the stresses in concrete. The stresses in steel are 10 times the stresses in concrete. Or you can just put it here, and then EC times 10 equals to ES. So modular ratio gives us an implication what are the stresses in concrete, and then from the ratio we can identify that the stresses in steel are like 10 times, or depends on the modular ratio, and both of them depends on the modulus of Fc prime. The concrete depends on the Fc prime, and the modulus of steel is almost fixed, 200 gigapascal. Anyway, so going back here, we'll talk about this now, and we'll give some explanation and calculation. Just want to mention here before I forget that the cracks in the beam here does not necessarily mean that the beam is going to fail, right? Concrete here is cracked and the tension is taken by steel. This is what does it mean? That it's going to do through this stage. And then when the cracks goes above and the concrete is totally crushed, that means a failure. Alright? Okay. So let's take the next portion here, which is the one we talked about. This is the one that will introduce us to transformed area. Transformed method. What's the transformed method? Okay, so it's simply when we have a beam, we are transforming the steel to a beam. We're transforming the steel to concrete in order to compute the stresses. Let's look at the next slide. Right, we are here. We have two beams. These two beams are reinforced beams. These are the rebars, right? And this is a beam. When we transform it, I mean, when we want to put it in a diagram or to explain it, this is the neutral axis, right, or the centroid of the beam, neutral axis, and here the rebars are replaced by something called NAS. N is the modular ratio, and AS is the steel area. Why do we do that? Because we want to compute. This is a method to compute the stresses in steel and concrete. We transform the whole section to concrete, right? And then we compute the stresses in concrete, and then by the modular ratio we can compute the stresses in steel, right? So this is the first thing. Second, we want to also to understand here, let's go back here, that this is the stress strain diagram. We have stress in concrete, then it goes to steel, Fs over N Fc. By taking an example, let's take an example to understand what is going on. To solve such a problem, in order to understand or to compute the stresses, we have to take an example. But we have steps that we have to follow in order to compute any example. First step to compute the stresses is we have to determine where is the neutral axis of the object. Second step, I mean by calculate neutral axis because the neutral axis moves up. It's not always in the middle. Because of the cracks and the tension, it can move up and keep moving up. Because what does it mean moving up? That means the concrete section is crushing and the stresses are taking place by the steel. So this this diagram in a point can be something like that. That means the stresses is taken by steel and the concrete is just almost nothing. Most of it is tension and then it's just a small compression. So the neutral axis is somewhere here. Here in this middle point. Whereas in this one it's in the middle, and so on. Second, we have to calculate something called first moment of inertia. Sorry. First moment of inertia. Right, what does it mean? I mean, we took it in statics. It's that's a really basic engineering. That means it's the area of a section multiplied by the distance of its centroid to the neutral axis. We'll see it in the calculation. Then calculate the second moment of inertia. Second moment of inertia. Sorry, this is of area, not inertia. Then we calculate second moment of area, or what is known as moment of inertia, I. Fourth, from these two, we'll have a quadratic equation. Solve it. Solve the quadratic equation. And the last step is compute the stresses. Okay, the best thing to understand any example, any formula, anything, is to have an example. Let's have an example, guys. Okay, I want to change the color. Change the color. Right. Okay. We have a beam here. This beam actually has an area, assuming 3 inches square. I mean by the area is the steel area. 3 inches square, actually it is 3 bar 9. That's the number, diameter number 9, and it's three of it. Okay, the width of the beam is 12 inch. Okay, and its depth is 17 inch. Let's do it from here actually. 17 inch, and the cover will take it 3 inch, because the cover plus the 17 gives you the full depth of the beam. Okay, compute the bending stresses in the steel and concrete for a given moment, which is 70 kilopound foot. And let's assume n is 9. And I told you, if this is not even given, we can get it. We can get it. Just EC is, as I told you, 57,000 radical FC prime. You can get it, and then ES is fixed, 200 gigapascal. So even if this is not given, you can compute it, but you have to have the FC prime. And of course, in this example, there's no need to give the FC prime. I'm just giving you the N directly, right? So the first thing that we have to do is first transform this beam section to this. So what do we have here? We have here 12 is the width, right? From the distance from here, from the surface of compression till the neutral axis is x, because we don't know where is the neutral axis. We are assuming it's at x distance. This is the neutral axis. So this one is actually 17 minus x. And this area is NAS. And N is 9, and AS is 3. That means it is 3 times 9, 27. That means it's 27. Alright, so we'll go to this first moment of area. First moment of area is the first, we'll go, so the compression should equal the tension for equilibrium. So the first moment of inertia for here, which is above the neutral axis, should be equal to the one below the neutral axis. This is from statics. So 12x is the area multiplied by the distance from the centroid of an object till the neutral axis, which is x over 2. Right? Should equals the area 27. Alright, multiply by the distance 17 minus x. Simply solve for x, which is equal to 6.78 inch. Great. So we know now where's the neutral axis. That's what's important. Let's draw it here quickly. Just draw it here quickly. What does it mean? It means that the beam is here, right? We have it here. The neutral axis is here. From 6.78. That's the neutral axis. So this is 10.22. So we understand now where is it. It's actually almost in the middle. So there are not, giving you indication it's almost in the middle. That means it's still not yielded. We are in the service stage, because if it is really yielded, the neutral axis would be somewhere here up. We're going to talk about this next lecture. All right. So that's the neutral axis. Fine. So what's the third step? Is to compute the I. So 3. Let's compute I. I is the second moment of area, or moment of inertia. We all know what's moment of inertia, but moment of inertia around the neutral axis. So for this object, we all know that the moment of inertia for a box or a rectangle, but on its base, not in the centroid, is b h cube over 3, not over 12, because it's in around its surface, plus, okay, plus, if we take about here, b h cube over 12, b h cube over 12 is nothing, because h here is nothing. It's just a small. But we all know that if we want to transfer this moment of inertia to the centroid from statics, it will be the I is equals A, which is the area, plus, right? sorry, AD square plus BH cube over 12. To transfer this one, it's BH cube over 12. To transfer it to the neutral axis, it's A, which is the area, multiplied by D square, the distance. Since BH cube over 12 is neglected because it's a small, H is a small, B is, it's just a strip, so it's neglected. So it's just AD square. So A times D square, which is 10.22. 17 minus X, which, now this is X. B is 12, H cube is 6.78 over 3. If you do the math, we will have 4067 inch power 4. Okay, once you get I, this is I, moment of inertia. That's it. We have just to calculate the stresses. Okay, we can do this number 4 and number 5 in one step. So 4 and 5 step. So stresses in concrete is what? Is moment that is exerted, which is my. Let's do my over I. M is 70,000 multiplied by it's the distance, which is X, 6.78, because there's a relative compression, and compression is above, is here. We always, guys, have compression, tension. Alright, over I, but multiply by 12 to transfer the units. I don't want it to be in feet. The moment here is in feet. I want it to be in inch. Okay, so it's equal 1,400 psi. Okay, what about the stress in steel? It is the same, my over I, but multiply by n. Okay, and when we do that, it is 7,000 multiplied by 12 multiplied by 10.22 over 4067, and it's equal to 18998 psi. Okay, so we have computed the stresses in steel and the stresses in concrete, and we can see that the stresses in steel are really higher, multiple times, than the stresses in concrete. So this is the way to compute the stresses in steel and concrete using transformed area. Okay, so let's take another example, saying which stress will judge the design. Okay, let's do something here. We'll talk about the example now, but I have something to explain before. Let's start right here. So assuming I have the same example as the previous example, but I have FC prime, stresses in concrete is 1350 psi instead of 1400, and stress in steel is actually 20,000 psi. Now I want to judge which stress, which one is it, the concrete or the steel, that the moment, if I calculate that, it will judge the section. Which one governs? If I have these two stresses in the concrete and in steel, and I want to design something, do I design based on the stresses in steel or based on the stresses in concrete? So from here we have to calculate the moment. So let's say the moment in concrete is the stress, right, multiplied by the I, which is the one we computed previously for 0.67, over the 6.78, which is the centroid distance, multiplied by 12,000 as a conversion factor to kilofoot, right? Then we will have 67.5 k-foot. If you want to do the same for steel, 27,000 multiply 4067 divided by 10.22 multiplied by n, which is 9, multiplied by 12,000 for unit conversion. This will give me 73.7 kilofoot. So here we can see the moment in concrete is less than the moment in steel. That means when we design, we have to design to this, because this really governs. This governs the design, because when the stresses reaches this limit in concrete, that means that's the concrete maximum stress limit. But when we keep stressing the beam and the steel can take more, like it's going, I mean the steel can take up to 73, but actually you're overstressing the concrete, and the concrete will be totally crushed. That means we have to design or take consideration for this number, 67.5. Okay, one more thing I have to talk about in this presentation now, that what if we have doubly reinforced beams? We have doubly reinforced. The term means that we have reinforcement here, tension, and we have a compression reinforcement. When we transform it and we put the neutral axis, which is somewhere here, right? So what do we do? That's the neutral axis, right here. So that means you have, this is NAS, as we know, NAS when you transform it, and this is the concrete. But these two are referred as, or are computed as 2n minus 1 multiplied by AS, and we put a prime to indicate that it's the compression side. So this is the way that we compute. So we compute this normally as the concrete, as we did in the previous example. This is just, we do the same, but we have to add 2n minus 1 AS prime as an indication for the bars. Why 2n minus 1? Because 2n is because of this, 2n AS, because if you, it means it is 2n multiplied by AS prime minus AS prime. If you break the parentheses, right, this, what does it mean? 2n AS prime is because we have an AS prime here and AS prime here, so it's 2, right? But why we subtracted AS prime again? Because when we calculate the concrete, we are calculating the concrete here assuming there are no bars, right? No holes. But actually there are, because of the steel. So filling these holes or taking out these holes, that means we have to subtract from the concrete, or we have to subtract from them AS prime. This, what does it mean? So when you calculate the concrete, we calculate it as normal, that doesn't have any holes, and we put 2n minus 1 AS prime here. But because we actually have one, it does, so we have to reduce the size of the holes, or the holes itself, from the compression side, and just put it in the tension side. Put it as 2n minus 1 AS prime. This is what we want to talk about today. Hope you enjoyed the video, and if you have any question, you can write it in the comments and I will answer it. Thank you so much.